Alright, this video is to help introduce the concept of Euler approximations for differential equation solutions. So before we look at Euler approximations, let's review a simple differential equation and how it's solved. If the variables are separable, we separate the variables, the y's and the dy's, the x's and the dx's, and we integrate both sides. And this produces a general solution to the differential equation. If there is an initial condition, as there is here, an initial condition, we can find a particular solution to the differential equation by substituting in the x and y values to find the value of the constant. In this case, the constant is rolled into the coefficient on the e to the x or exponential growth function, and this represents a particular solution based on the given condition for that differential equation. Now, substituting in a variety of values for x, starting with 0, and that gives us an initial condition, and going up by a quarter, we can find actual approximations or actual solutions to the differential equation at specific values for x. So these are known values, and here is a list or a picture of all the different solutions to the differential equation as demonstrated. Now let's work under a hypothetical. What if we actually did not know the solution to this differential equation? In some cases we can't find the solution to the differential equation. What we can do is approximate using Euler approximations. This is a method that Leonard Euler developed and he got named after. And in order to do Euler approximations, we need to have pretty methodical, organized algorithm set up. So the first thing we must definitely do, and this is for IB, if you make this table, you're going to get a lot of credit for your Euler approximations. So we're going to start with defining our x's and going up by the appropriate steps. Usually the step will be indicated by 0.1 or 0.25 or 1. Whatever the steps are, you'll set your x column to go up by those increments. The y values will be determined by both the previous y value and the rate of change at that particular point. So what we're going to do here essentially is determine what the slope of the tangent line is at the given point. And so we do so by using the differential equation given. dy dx is the slope of the tangent, and all we need to do is substitute in x and y. In this case there's only a y. So we substitute the 2 in for y times the 0.3, tells us that the differential equation will have a slope of a tangent of 0.6 at the initial point. Now, what we can do here is pretend that the next point in the solution is going to lie along the line in the direction of this slope. So we're going to head off in a direction of 0.6. That's where the dy dx comes in. But we're only going to head along that line for a change in x. That is to say, we're only going to go there for a quarter of an x away from the original y value. So we're going to take our initial y value and add the slope for just a quarter of a unit. So these are the values that belong there. And that gives us an approximate y value of 2.15, 1/4 away from the initial y value. So using our new y value, we can establish a new rate of change. And so now we know that the curve is going to be steeper at 0.25 than it was before by a little bit. And our next x value is going to be a quarter away from its previous value. To find the next y value, we take our previous y value, 2.15, and we go in the direction of our slope for just a quarter of an x longer to produce a second y value of 2.31125 approximately. Again, this is an algorithm and it's a recursive algorithm, so this tells me now we are steeper 1/2 unit away from where we started, and we can use increment, another 0.25, to determine where our next y value is going to be. So once again, we notice here we take the old y value plus the slope times the increment, and that gives us our new y value. Our new y value gives us a new slope, and we take the old y value and add to it the new slope for just a quarter of a unit. And y is approximately 2.679 right there. So what you see in the graph here is a visualization of the first two Euler approximations going over a quarter and up. And I'm going to make the data table with all my approximations here, and these are all the actual solutions, and that's what we found using the integration technique. And we can see that in the beginning, 2.15 and 2.1558, there's not much of a difference from the approximation to the actual value. The further along the chain we go, the further away we're going to be from the initial value, the correct solution. But as we can see, if we use very small increments, we're going to get really accurate solutions that represent solutions to the differential equation. In Euler's method, of course, what we'll probably do is allow the change in x to approach 0, and therefore we can find the solution to the differential equation using some sort of limit argument. Just to drive the algorithm home, let's take a different step value. Instead of a quarter, we're going to go with 0.1 rather. And instead of using a differential equation with just y's in it, we have a differential equation as shown. So this differential equation shows us that the slope of the tangent is dependent on both x and y. We're given the initial condition of 0, 1, so I use those for my first 2 points, and I use those 2 points to determine the slope of the tangent at that location. My next y value is going to be achieved by taking the first y value. Let me let this write out. So if we take the first y value and add the slope just for an increment, so we're basically going to take away 1/10 from our initial y value to get an approximate 0.9 is the y value solution 1/10 away from our initial condition. Using both 0.9 and 0.1, x squared minus y squared, we can achieve negative 0.8 as our new slope of a tangent, so we're now less steep but still decreasing. So we again go up one more 1/10, so we're now at 0.2 for the x, and we are going to continue, take the previous y value plus the slope times the increment, and that will give us the next y approximation, use the y and the x to determine our new slope, use the previous y value plus the slope times the increment to get the next y value, use the y value and the next x to determine your new slope. So you can see this becomes really repetitive, but it's also algorithmic, and this is something that you can easily program a software to do for you. I'm sure it's out there somewhere. I should probably look for that. I will. Anyway, as you can see, keep repeating and repeating until you get to your target, and we are trying to approximate y of 0.4. And when x equals 0.4, we can approximate y as 0.708. I went to 3 sig figs after I rounded, so now I know that this is the approximate value of y of 0.4 for this unsolvable differential equation.